The Webb glance is such a long way out that it's catching light that has been voyaging for north of 13 billion years. Yet the universe has been extending, and thus the light has been extending. For the most distant worlds, we're thinking back, in time nearly to the Big Bang. The immensity of the universe might seem vast, but it began in its entirety from what we allude to as the singularity. As of now, this is how we might interpret the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy discoveries made by the JWST might actually alter our perception of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the recognized NASA executive James E. Webb, remains as a wonder in current galactic investigation. This telescope represents a huge mechanical leap forward from its ancestor, the Hubble Space Telescope, coming about because of a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The JWST surpasses the abilities of its predecessor. It utilizes cutting-edge technology and a design enhanced for concentrating on the universe in remarkable detail. Not at all like the Hubble, the JWST conveys clear and sharp pictures of far-off heavenly bodies, working primarily in the infrared range. This interesting component permits it to infiltrate astronomical residue and catch divine items that were, beforehand, stowed away from our view. With its giant 6.5-meter essential mirror made out of 18 hexagonal sections, the JWST diminutive people the Hubble's reflector size. Situated roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it circles the Sun in a state of harmony with Earth, guaranteeing a steady and continuous view of the universe. While looking into the universe's farthest reaches, it comes from light years and also involves a type of time travel. The JWST uses infrared instruments to notice heavenly objects and events going back billions of years. The light emitted by these objects, because of the expanding universe, goes through a redshift, moving from the apparent range to the infrared frequency or longer wavelengths. Luckily, infrared light can be identified by the JWST, radiated by heavenly bodies at extreme distances, empowering researchers to study the introduction of stars, investigate cosmic system development, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of cosmic structures at the outer edge of the discernible universe. This finding challenges the validity of the theory of how things came to be, provoking a reassessment of our key cosmological assumptions. To better understand how we arrived at this point, we should take a brief tour through the history of space. Investigation. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by noticing divine bodies. Newton's regulations in the 17th century provided a hypothetical space structure. Travel in the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space science. His observations uncovered that far-off nebulae were distant, isolated worlds, not part of the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were moving away at higher rates, giving proof to the expansion of the universe. The post-World War II history of space exploration marked the start of the race for space with the Sputnik of the Soviet Union in 1957 as the first orbiting artificial satellite, Yuri Gagarin's 1961 trip to space, and the Apollo 11 moon landing in 1969 as crucial accomplishments. Fast forward to 1990, when the Hubble Space Telescope was launched, giving unprecedented clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of how we might interpret the universe. It uncovered the boundlessness of space and changed fundamental thoughts in astronomy. Take the Hubble Space Telescope, JWST, for instance. It snapped the famous Pillars of Creation image in the Eagle Nebula, displaying a star nursery created by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field, capturing a huge number of galaxies in what seemed like a void patch of space. The HST also dove into exoplanet atmospheres, pinpointing components like water and organic molecules in distant worlds, alluding to the possibility of zones that are habitable beyond our solar system. Following the development of the closest observed supernova, SN 1987A, it shed light on the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a foundation of modern cosmology, dazzling the world with its amazing innovations. In its replacement, the James Webb Space Telescope was launched to expand on the technological advancements and lessons learned from previous models. Our understanding of the universe's origins is explained by the prevailing theory of the universe's origin. Around 13.8 billion years ago, the universe started as a seriously hot and dense singularity, quickly expanding and giving rise to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures that can be seen today. The Big Bang theory also explains cosmic light from microwave background radiation, element abundance, and the large-scale structure of the universe. Despite being widely accepted now, the Big Bang theory faced skepticism and challenges in its beginning. Alternative models, like the steady-state theory, proposed that the universe was without a specific beginning. Concerns regarding the evidence supporting the initial singularity, expansion, and observed anomalies arose. Most of these objections were addressed over time, and an important piece of evidence appeared as a result of the discovery of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, alongside technological advancements, further supported the theory. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can look through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared abilities allow it to concentrate on star-forming regions, celestial nurseries, and the formation of stars hidden from optical focuses. Infrared light, through longer wavelengths compared to visible light, can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects that emit primarily in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies as celestial bodies move away from them. Light waves get stretched, causing a shift toward longer wavelengths. The JWST's wavelengths are referred to as redshift. These can be detected using infrared capabilities, redshifted signals, capturing light from the early universe and offering insights into its formation and evolution are significant. Energetic events, like black hole mergers or new star births, primarily emit in the infrared range, further expanding the JWST's investigative capabilities. The telescope can explore phenomena that would otherwise be hidden or invisible. The JWST supplements optical telescopes, like Hubble, by having enhanced sensitivity and the ability to detect infrared radiation. This ability allows it to dig and look further into space, deeper into astronomical history, revealing hidden astronomical wonders and offering a more comprehensive perspective of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Recently, it disclosed something so mind-blowing that it might prompt a reconsideration of the entire cosmological model of the universe. We've discovered enormous masses of galaxies at the very edge of the ancient universe that could be seen. Galaxies existed just a few 100 million years after the Big Bang. The baffling aspect of the cosmic dawn is that we're unsure about how early in the universe's history such enormous structures formed. This discovery might cause us to reevaluate our understanding of the formation and the early evolution of the universe's galaxies. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions regarding the fundamental character of the universe, including its composition, structure, and the forces governing its evolution. As the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main restriction was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar gas and dust. The James Webb Space Telescope represents a significant leap ahead in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that came into existence within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity in order to comprehend the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked ferocious debates in the scientific community. JWST observations have uncovered a greater number of galaxies in the beginning of the universe than anticipated by existing models, suggesting a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models, predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations provide fascinating options and questions for additional research. The existence of large structures challenges early models of cosmic structure formation, prompting scientists to improve models for a better explanation. Understanding how these massive structures quickly grew after the Big Bang, a conundrum that necessitates an explanation, does not go against basic principles of cosmology. Significant disparities in the conditions of the early universe, in contrast to predictions made using existing models, have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can say is that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but in-depth investigation sometimes reveals differences. For example, early observations may show specific properties or arrangements within distant galaxies that, upon more apparent examination, reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of bodies of the universe to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium, in line with theoretical expectations. However, spectroscopic examination with the JWST revealed fascinating differences in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This defies conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations indicating a relatively consistent pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies.